That's right. We can see and hear you, Matt. So our next speaker, our final speaker of this half of the session, and then we'll have a 45-minute break. Our final speaker is Matt Malkan, who is going to talk about Passage. And take it ahead, Matt.
Thanks. Last speaker in between you and your coffee. Greetings from UCLA. I don't think I have to convince anybody now, if you've been listening to the previous talks, that if you want to understand high redshifts and the era of recombination, you just cannot do this without spectroscopy. We're talking about in the infrared. And you also realize if you want to do a survey with JW, you have to take advantage of its unique capability for slitless spectroscopy. So you get all of the spectra of everything in the field in one shot. Can never be done from the ground ever because of the air glow of the atmosphere. So this was all known. To show an introductory slide about the background, what was previously done. There's not much to show you. The idea of slitless spectroscopy was, of course, pioneered with the Wide-Field Camera 3 on Hubble Space Telescope, but in all honesty, trying to go for high redshift, for example, Lyman Alpha emitters, was just at the limit of what you could do. Now, the one thing that, even if you're sold about, yes, infrared slitless spectroscopy from space, you got all of that, what you might not be sold on is, let's do this without any JWST observing time, because that's too valuable to take. Oh, of course, you should. I'm just kidding a little bit. But the telescope and the NIRISS instrument was really designed with a lot of thought put into how you could do pure parallel infrared slitless spectroscopy, as we, the WISP team, had done with WIFC3. WISP being an acronym of acronyms, WIFC3 infrared spectroscopic parallels. This is about as far as WISP was able to get with a few galaxies with Lyman Alpha emission it's interesting, up to about redshift to 6.4, even though it was more sensitive at higher redshift, did not find anything. We just don't know what the high luminosity tail of this luminosity function is. But anyway, who cares? Whatever's been done. I mean, JWST with NIRISS is such a ridiculous game changer that honestly, all bets are off. Now, it appears that you cannot have a project here without a good acronym. We've struggled with that a lot. An acronym that is not itself made up of acronyms. So here's our best attempt. So PASSAGE, in case y'all don't remember, stands for Parallel Application of Slitless Spectroscopy to Analyze Galaxy Evolution. Right, the important point is parallel slitless spectroscopy. And so you can see the picture here from one of our team meetings. And we're trying to navigate this passage. On the one side, we don't want to bump into the rocks of not having enough sensitivity to do this project. On the other hand, we don't want to bump into the rocks of not covering enough fields. And we're trying to thread the needle with this Pure Parallels project. And well, as you probably realize, when you're doing slitless spectroscopy infrared, there are many, many science goals far beyond what this team anticipates doing. And the goals that took most of the proposal, or the more pages, were actually the so-called intermediate redshift of 3 and 4 galaxy science with emission lines and absorption lines. But there was a section which I think a lot of people liked about end of recombination, well, era of recombination galaxies, particularly looking for Lyman Alpha and Lyman breaks spectroscopically at redshifts 7 and up. And just want to put the names on here. You know a lot of these people, but what you might not realize is, these are some of the most friendly and collaborative people you're just going to find anywhere. Man, if I were a young person right now, if I were a middle-aged person, anything kind of person here, I would really get in touch with any of these people. The chances are very strong that you've got a great idea here that this team of good folks is not going to be able to pursue with this project, and we'd love to talk with you about it. I think it would be very productive. I mean, I'll be disappointed if most of the science that comes from PASSAGE is done by these team members. That's not what's going to happen. Actually, it's going to be you folks. So obviously you want to detect Lyman alpha emission. And so we've really tailored or torqued the program to emphasize that by putting most of the entire exposure time is into the shorter wavelength F115 GRISM specifically for that purpose. And so this is the kind of sensitivity that you can get when you put most of the time into this 115 GRISM, from 1 micron to 1.3. And even Lyman alpha emissions, well, even if there's no continuum there at all, we feel like we can get down, or if there's a lot of continuum, we feel like we can get down to pretty sensitive levels, at least for the brighter Lyman alpha emitters in these randomly selected fields. And so there's a few specs. It's also very important that we're spending additional time in each of these visits getting the supporting imaging in each of those 3 bands. So we should have detections for everything in the broadband filters, unless it has a very, very high equivalent width, but we're looking for those as well. And this is rather important, we'll have the continuous spectral coverage all the way out to 2.25 microns. Of course, it's for a lot of other science purposes, so that we can separate out and distinguish the true high redshift galaxies from the intermediate redshift interloper galaxies. So what was mentioned actually briefly, and people might not appreciate, we don't actually need emission lines here to do interesting things. These are some simulations of some of the, sort of a typical field at 26.6 magnitude and a deeper field at 27 magnitude. And we believe that not only can we detect the break at the Lyman limit, for example, at a redshift 8 star-forming galaxy, and then we can distinguish it, for example, from a redshift 2 interloper. There's a bomber break there where you actually detect emission lines and you detect continuum. Even a quiescent galaxy that's an interloper, we detect the continuum beyond the Lyman break, proving that it's not a Lyman break galaxy. And the PDFs of the redshifts say that this is going to work, at least for the brighter, very high redshift galaxies. This is an estimate from Alexa Morales about what emission line, that is Lyman alpha galaxies, will be detected here. Now, this is not exactly what we ended up with in the final passage parallels. It's a little bit of guesswork as to how many pure parallels we could get. We were very conservative, very cautious about this. We're only looking at the parallels that are done with NIRCam and MIRI as the primary instrument. I think we'll go deeper than this because we're spending a lot more than 2 hours. In fact, we don't even get started on the Lyman alpha search until we're spending several hours on it. But, and I don't know how many fields we're going to get. We're still in communication. The big question is not, there's just tons of pure parallel opportunities. The big question is how many calibration fields or frames will the Institute decide to take. But anyway, we really have the sensitivity, of course, depending on how many Lyman alpha emitters there are at redshifts 8, 9, and 10, to have reasonable samples. And the particularly strong selling point here is that these are going to be in dozens, maybe if we're lucky, 40 or something fields all over the sky randomly, because we're very, very concerned, and you've seen why, about the cosmic variance of the EOR galaxies and Lyman alpha emitters and so on. So the estimates, well, you can take these with a grain of salt. They're very uncertain, but I think we're going to have dozens, maybe 60 Lyman alpha emitters above a redshift of 7, and you get the imaging, and you get a lot of other things you'd like to know as well, far UV slopes. One thing we're very excited about is getting some of the other metal emission lines at longer wavelengths at the same time. And of course, those can be gotten even at redshifts approaching the era of recombination, redshifts of 5 and 6 and so on, which we're interested in that as well. And then finally, I just said this actually, but to remind you, of course, we feel that we're entirely complementary to the deep surveys that are just going to do brilliant work on relatively small fields in one place. And you can see it's a little bit of a matter of luck. You've seen a lot of these simulations. whether those fields will hit relatively neutral and rather opaque regions of the IGM, or whether you might get lucky and fall in one of these regions with a lot of UV bright sources, which will open up ionized bubbles, in which case we'll see lots and lots of Lyman Alpha emitters, those gray objects that we're looking for here. Let's see. So that, I'm sorry, I went a little bit quick over this, but that in an overview is what we're trying to do. So I guess I'll just go back to my first point again. Please do be in touch. Oh, there's one more point here. We've gone to a lot of trouble in the proposal to say just how hard we're going to work on releasing the data as fast as we can and as completely as we can to the community. That's really our main goal, as I said here, no proprietary period on these pure parallels. So we'll almost immediately reduce and release images and spectra, 1D spectra, but we're also planning, now of course this depends on whether we get our modest funding request approved for this. It's in the proposal. We want to do high-level science product releases. For example, metallicity determination, not just redshift determinations, line flux and so on, but metallicity from line ratio maps of resolved galaxies. That's something we'd like to provide to the community. To give you an example of how seriously we want to do this. There are many other related projects for people who are interested in reionization. We want to look at leakage of Lyman continuum photons. We're interested, of course, in magnesium-2 emission lines at more intermediate redshifts as a proxy for leaking Lyman continuum emission. And obviously, if for every Lyman alpha emitter that we can get our hands on, we want to look at the spatial extent of the Lyman alpha. With JWST, we're not assuming that everything is a point source. I'm not sure there's going to be all that many point sources left after JWST gets a hold of these deep observations with this incredible resolution. One other thing I just wanted to mention, because it came up in the chat, we're planning for every one of these fields to have orthogonal orientations of the grism. So we'll have half the data with the spectra running this way, and some of the spectra will be on top of each other. We know that. We have tools that we're going to try to decontaminate them. It's tricky. I think we'll be able to, actually. But we'll then also, for those ones that are hopelessly contaminated, we'll have the orthogonal orientation of the grism to see which emission lines are coming from which object. I think we're really in pretty good shape on that. Quite a lot of attention is being given to that. So does that leave time for questions?
Yeah, thanks, Mark. I think we've got just a minute or two for some questions, and I know there's some questions in the chat. So Steve, do you want to ask the first?
Consider strategies to address possible differential magnification. What a cool idea. In case the emission lines, the continuum are spatial. So I love that. Yeah, we've been discussing this quite a bit at JWST resolution. You cannot assume, in fact, this is a very crucial science question, that you want to extract your spectrum of your emission line with exactly the same aperture that you determine from the broadband continuum. So we've got the tools to do that. That might not be in the first data releases. In other words, you have to get into the data to try to decide where the centroid of the emission line or what the distribution of emission line gas is. But so the data are definitely going to be provided. What we're trying to do basically is to provide fully reduced and calibrated data cubes. So anybody will be able to come in and say, okay, including us, of course, we want to make emission line maps and compare them to the possibly different maps of the starlight in resolved galaxies. Now, we didn't go on about that at very high redshifts too much, but it could be an effect there. Certainly going to be a very important effect for all of our redshift 2 and 3 galaxies. So yes, very good question.
And Matt, I'll ask you. I'm sorry, Steve.
No, go ahead.
All right, I'll ask you another question. Are peer parallel surveys biased by the fact that overdense regions may be targeted preferentially in the primary field?
Very good question. Yeah, by the way, I did want to point out about bias. We're not doing any photometric preselection. We want to know, for example, the true distribution of Lyman Alpha emitters in the sky without any photometric preselection. But an interesting point, we're at high latitude fields, not in the galactic plane. I don't know. There's a lot of observations of people. We've gone through all of the GTO observations. A lot of people are doing stuff like exoplanets and stuff like that. I guess people are interested in that. So it's not as biased as you might think that will be. Yes, there's a few famous fields. Of course, many of the famous fields, they've already took their parallel observations and incorporated them into attached to the primary. So we'll look at that. Of course, we can go back, if we really do have 40 or 45 fields, we can go back and construct less, basically unbiased samples that were not chosen because it's near a famous deep field. But there's a lot less of that than you would think, actually. Darn good question, though.
Thanks for that, Matt. There is a few more questions in the Slack, which I've just tagged you on. If you don't mind answering those in the Slack later, that'd be great.